All right, so I'm going to keep going through some of these practice exams. If you have specific problems, I can kind of go over those or start with those. Otherwise, I'll probably pick and choose and kind of dance around a little bit. So just before we kind of get going, I did, I think on Friday, get kind of your Learn Smart with the lowest drop. After today, tomorrow, when I get to the office, you kind of have those final two homeworks. If you wanted to do those and kind of improve on your grade, or like I said, I dropped the lowest one. So if you've done the first 4 Excels and 5 Connects, you really don't have to do those. They just be your lowest grade and they get dropped. But for those who do them, I'll kind of grade those as quickly as possible and get that Excel and Connect grade with the lowest dropped up there as well. So you'll then have like a really good idea of what your grade is going into that final. For this class, I believe the final is Thursday at 9:45. Let's see if so Thursday at 9:45 is our kind of given time slot. That'll be here in this room. You'll have 2 hours, I think. Right now, I believe it's 24 problems. So that's kind of where I ended on. So a few more problems than maybe the other 2 exams, but we've got an entire additional hour. It could have been maybe in, what we have twice as much time. So maybe I should have given you 40 problems, but I don't want time to be an issue on this final. I think it shouldn't be for anyone. I'll bring kind of ZT tables and that formula sheet for you. You can have extra paper and write on it. Kind of really, calculator, kind of like the other 2. But in terms of logistics, does anyone have any questions for me regarding the exam before we start in on some problems? Okay. Anybody have any particular problems on any of the practice exams? I know I kind of started going through the wrong one last class, so I actually saved that and put it back up as practice exam C. Just some additional problems if you want to go through those. Some of them might be repeated across the exams, but I know there's a few that aren't, so I kind of threw that up there as well as an additional resource. No specific questions? You guys trust me to kind of go over some? I guess I wrote the exam, so maybe I'd have a little bit of insight. So I think we didn't cover this type of a problem on practice exam A on Friday. So I want to make sure we kind of start there. So we've got this kind of set up where we're looking at the number of credit hours students take before and after some policy that charge per credit hour versus once you hit a certain limit, you don't have to pay any additional money. And so we've got 35 students. We look at the number of credits I took before and after. We calculate this difference variable, and we find that the average change was what? An additional 1.25 credits. Right? So we have this kind of mean difference, or we have the same 35 students, so we have this matched pairs example. Right? Excuse me. We then calculate the variance on that difference variable. We found that to be 13.2. And we want to test for whether or not the average difference has increased, right? So has that difference after the policy changed gone up, right? Is it positive? Okay. We assume the opposite is true, and then I kind of give you this alpha value of 0.05. So I first ask, if you wanted to calculate, what's the test statistic for this above hypothesis test? Well, if we go to our formula sheet, we kind of got our confidence intervals for our 2 population differences and our test statistics for 2 population differences. However, we had this matched pairs example. So here's our confidence interval equation for that. And here's our test statistic. Okay. So the test statistic for these matched pairs examples is actually, I think, a lot easier than those of the sample differences. Right. So all we have to do is kind of plug our values in. I think these matched pairs examples, I'm using the same notation every time, so hopefully it's not too bad to identify them. It's really just a matter of plugging our values in. So the sample difference we found was, I think, 1.25, right? The variance, so then we divide that by the square root of the variance over the sample size. So we go back, and I'm working off that practice exam C that I put up there as well, because I'm going to choose some other problems from there. So the variance was 13.2, and I had 35 individuals, so 13.2 over 35. Okay. And I just get this entered in my calculator, and really I'm done at this point. Now, One thing to point out is for every test statistic, remember, we're dividing by some standard deviation. This is the standard deviation of our mean difference. Actually, sorry, I don't use carets, I use a bar. So the standard deviation is always going to be positive. So whatever mean difference you find, that's going to tell you the sign of your statistic. So we saw a mean difference of 1.25 positive. So our test statistic should be positive as well. So when I was looking at those answers, I should rule C out right away. From there, it's going to have to be, I actually have to get this entered in my calculator. So if anyone was working along with me, if I do that, what do I end up getting here? I think it's 2.035. Is that right? Yeah, so I think approximately 2.035. Okay. So that one shouldn't be too bad. It should be maybe one of the easier questions on the exam. If we're then told, all right, find the p-value and the outcome of the hypothesis test if the test statistic you found was instead 1.307 and use that same alpha of 0.05. Well, if I only have a sample difference, kind of talked about Friday, this is going to be these mean difference problems, or it's going to be one where I have to use the student t. The only time I get to use a standard normal is if I'm comparing proportions or I have known population variances. Okay. So I look here, I have a sample size of 35. This isn't going to be one where I give you an assumed true degrees of freedom because we don't have to use that complicated formula. When we have matched pairs, we said it goes back to almost like, well, we really only have one population, the same 35 people. So my degrees of freedom goes back to simply being n-1. I'm kind of reminded of that in that formula sheet as well. So 34, right, would be my degrees of freedom, 35 minus 1. However, oops, I did not want to do that. However, my hypothesis test, I had a right-tailed test. Right? So I'm thinking about all of alphas in that right tail, right? So I want to find the critical value from a student t distribution that gives me the alpha of 0.05 in that upper right tail, and my degrees of freedom is 34. Okay. So I'll go to that student t table. Zoom in. I had 0.05 was the area I wanted in the tail. And then I go down here to my degrees of freedom of 34. So 1.691. Oh, actually, sorry. I was just looking up critical values. Well, we got an additional problem here that I didn't give you that I could actually ask you. So sorry, I was thinking critical values, right? So we did find the critical values, what, 1.6, was it 91, something like that? This problem instead asks you for the p-value, right? Well, if the test statistic you found was 1.307, which is kind of the assumed true value was given to you, the p-value would be the area to the right of that for a right-tailed test. Okay. So same sort of idea. If I go to my student t table, it's just now, instead of knowing the area in the tail, I have the test statistic, right? I have one of the t values. So I go to 34, 1.307, the area to the right of that would be 0.1. So my p-value is 0.1, right? So actually here we can solve this using the critical value or p-value approach. But if I was to use the p-value approach, since that's what the problem asked for, with a p-value of 0.1, remember our alpha was 0.05, we only reject if the p-value is less than alpha. So my p-value of 0.1, is that less than my alpha of 0.05? No, so I would say that I fail to reject the null. So my p-value would be 0.1 and I would fail to reject. Now, if instead I've been asked for the critical value approach, using that alpha value, I found my critical value of 1.691, right? But I had a test statistic of 1.307. So if I plotted my test statistic here, we would see that for a right-tailed test, my rejection region would be to the right. My test statistic wouldn't be in that rejection region. So either way, it would lead me to fail to reject the null. Okay. Any questions on that since I started out answering a question that wasn't even asked there? So I could ask you either of these or both. Well, I could ask you to find critical values for these matched pairs. I could ask you to find p-values. Now, if I ask you to find p-values, I'm going to give you one of those exact values that show up in the table. So for instance, I wouldn't tell you what's the p-value if we had a test statistic of 1.5, right? Because that's where we had to like put the p-value within a range because it's not one of the exact numbers up there. If I ask you for p-values with these matched pairs or any type of example that has a student t, I would give you one of these exact values that show up in the table, okay? Any questions on that one before we keep moving? I think that was the end of the matched pairs questions there. Okay, that. All right, so we're going to keep working off this practice exam C because I just want to go through some more linear regression stuff today since it's kind of the newer stuff. Probably we spent a little bit less time on it. We really, spent a lot of time on hypothesis testing. Before we kind of leave today, I'll kind of give you like what you should know for the exam, just some general subjects. But if we look here at this, GPA, where we played around with this in class, actually, let me see what we did in the class. So we did practice exam A last class, correct? So what was the example we had there? Okay, so we did a wage one there. So we're getting a slightly different example. So that's good. I think in practice exam B, it's a similar sort of regression with GPA. So that's the one that I kind of made videos and put up on YouTube, but I think it's still good. I might, give you some examples on the exam that are familiar. So this is a good one to go over. So let's say I've got my dependent or my Y variable of GPA, and I'm trying to predict it using these 5 things. Okay. So you come down here, how would I interpret this SAT variable? So 0.002. So how would I interpret that SAT coefficient? What's the general interpretation for a coefficient here? For every unit increase in my X variable, the predicted Y value changes by whatever that is, or goes up or down, right? Depending on if it's a positive or negative coefficient. So here, for every 1 additional point in the SAT score, we would see the GPA go up by 0.002, okay? And then because we have other variables that are in our regression, we are holding all those constant, right? So holding everything else constant, every additional point is correlated with a 0.002 increase in that predicted GPA. Now, let me make sure it's not one of the questions before I ask this. Okay. So how would I then, what if I had given you this output and said, what's the effect of scoring an additional 100 points on the SAT score? All you would have to do is, I like the unison, I love the answers, right? So we've got, if we know the effect of 1 unit, you just scale it up by multiplying it by however many units you're interested in. So here, yeah, multiply that by 100. So if I did 100 additional points in the SAT, predicted GPA would go up by 0.2, right? 0.002 times 100, okay? So that could be a question I ask, is kind of scaling some of those coefficients. And I think it asks you for the interpretation on the athlete variable, but it's going to be a similar sort of thing if we were to interpret the female variable, right? So why we I compare those two? Well, sometimes I said we might have these dummy or indicator variables. They're just 1s and 0s. So here, instead of the athlete variable, how would I interpret that female variable? A 1 unit change there would be what? Yeah, right. So it's whatever group is the 1 relative to the group that's 0, we would expect the predicted Y value to change by whatever that coefficient is. So here, if we're looking at an individual and they're female relative to a male, we would expect that their GPA would be 0.186 higher, holding everything else in the regression constant. Remember, which is pretty powerful, because what we're really saying is 2 people with the same SAT score, they're either both student athletes or not, they both have the same high school rank, both have the same number of total credit hours, but one of them is female, one of them is male. The female, we would expect about a 0.186 higher GPA. And then the athlete would be very similar. An athlete relative to a non-athlete, we would expect the predicted GPA to be about 0.16 higher, holding everything else in the regression constant. Okay? So that's how we interpret kind of dummy or indicator variable coefficients. So that's not too bad. Did I Yeah, we went over practice exam A, correct? So we didn't look at a high school ranking. We didn't talk about this, right? This is kind of a weird one. So here, how would I interpret this high school rank variable? So think about what's the best ranking in a high school? 1, right? So it's gonna be kind of like golf scores. It's kind of weird, right? Because our 1 unit increase is actually going from like the top student to the second best, right? So for every unit change, we're actually seeing someone fall in the ranking. So this is kind of where math and the way that we speak doesn't really line up, right? It's an increase in 1 unit, which actually means you're falling back in the rank. So if someone goes from first in their class to second, right, and falls back 1, we'd expect their GPA goes down by 0.003. Right? I probably won't give you one that difficult on the exam, but kind of pointing it out there. Sometimes we really have to stop and think about, what these variables are that we're interpreting and what they really mean, right? And going up by 1 unit in rank is actually a bad thing, right? So that the sign of that coefficient actually makes sense. Now, this is like an easy one. So if I'm looking at this, which of these variables could I say are significant? And doesn't really matter what level. Why doesn't it matter what level here? So if I look at those p-values, they're all basically, anytime I see that e to the negative, that's Excel's way of saying, well, we stored all these, decimals here, but you have to go out to the 142nd before you see anything other than 0, right? That means move the decimal 142 places to the left. All these p-values are essentially 0. So if all the p-values are essentially 0, which of these variables can I say have a significant relationship with the y variable of GPA? Athlete for sure, right? 0.0001 is going to be less than any alpha I choose. So let's think about kind of what we're doing here. With any coefficient, we always start out assuming what? That it's equal to 0. This is always our hypothesis test when it came to these coefficients. So I'm always going to have what type of test? Yeah, two-tailed test, right? And what this is really saying is my null hypothesis is that there's no relationship. So if I can find a p-value that's less than alpha, I can reject the null. And by rejecting that there's no relationship, really, when I find a low p-value and reject the null, what I'm really saying is I found evidence that there is a significant relationship between that x and y variable. So if all my p-values are approximately 0, it doesn't matter what level of confidence I want to use or level of significance, right? I could use an alpha of 0.1, 0.05, or 0.01. And for all levels, I'm going to be able to reject the null. So no matter what alpha I choose, I can reject the null and say that there's a significant relationship between GPA and every single one of these variables, okay? So one way to kind of prevent yourself from making an easy mistake where you look at this and say, oh, 1.46 times e to the negative 24. Well, that's definitely not going to be less than an alpha of 0.1 or 0.05. Well, no, remember, p-values represent probabilities. So how could I ever have a p-value that was above 1? Well, I don't. I have to look, oh, yeah, e to the negative means move that decimal 24 places to the left. Okay. I think that was a question. Oh, maybe not. Maybe I just threw that one in there, right? But that is likely something, wink, wink, I could ask you to do, right? From some Excel output that I give you. I think I had somebody ask a question. I don't know if it was this section or another. I'm not like making you run any regressions, right? You don't have to have like a computer or anything in front of you, but I would do something like this where I give you that Excel output, right? From a regression that was ran. I think the next question asks, how would I interpret the intercept here? So how would I interpret the intercept coefficient? Yep. So remember, when I have this regression equation up here, once I obtain values for each one of these coefficients, right, then I could predict what GPA is if I gave you a hypothetical person, right? So if I gave you, someone with a 1200 SAT who wasn't a student athlete, ranked 15th in their high school, et cetera, all you would do is plug in those values you had for the coefficient on every variable, multiply them by this hypothetical person's values for these different X variables, and then add them all up. So after the due date today, I'll put an answer key up to that 5th Excel assignment. There was a similar question there. So on top of these practice problems, if you want to go to that, because really the last Excel assignment, most of the Excel work was just running the regressions. Then it was a lot of interpretation and different questions. So that might be another good study tool to look for tomorrow morning. Okay. Or I'll probably actually have it set to time like at 1 o'clock tonight or something so that it releases. But so for the intercept, if every one of those variables is equal to 0, then it doesn't matter what the coefficients are. Anything times 0 plus anything times 0 is just going to always add up to 0. The only thing you'd be left with if all the X variables were equal to 0 would be the value of that intercept. Okay. So that's why the interpretation is for an individual with, 0 SAT score, ranked 0 in their high school. And these interpretations will be kind of wacky, right? Like you can't really be ranked 0 in your high school, but it's almost like, even though we never see these X values in the data, we have to, like, if you have a line of best fit, it has to start somewhere. And it's hard to visualize this because we've got more than one variable. So this line is like really not anything we can visualize per se. But that's still how we interpret it. Okay. What if I wanted to find test statistics here? Well, if I go to my formula sheet, anytime I'm asked for test statistics, this should be like the easiest problem on the exam. All I do is take my coefficient estimate and divide it by the associated standard error. So if I'm looking at the athlete variable here, 0.16 divided by 0.043. So that's going to be what? Approximately 4. So my guess is the exact value is going to be 3.7. Right? I just did that by eyeballing, kind of rounding. But if you wanted to find the test statistic for any of these, I just put a text box over these. You could actually recreate all these if you wanted to. So sure enough, 3.75-ish. So I asked you for a test statistic. That should be hopefully some easier points in the exam there, right? And that's on the formula sheet as well, right? It kind of reminds you, it's just take that coefficient, divide it by the standard error. And this equation here is kind of what I was talking about when you're making predictions, right? Once you have those coefficients, plug those in, and then just plug in the X values for this hypothetical person or company or county, whatever the example ends up being. Okay. Oh, where were we? All right. So that kind of gets through the questions that were asked here. Instead of these, I'm going to ask something slightly different. So let's instead assume you saw this and I said, either what's the interpretation of your R squared, or maybe I just asked the general question, how much of the variation in GPA do the variables of SAT, student athlete, high school rank, female, total credit hours explain? So the definition of our R squared is the proportion of the variation in our Y variable that the X variables we included in our regression explain. So here, 27%, if I want to translate that into a percentage, right? R squared is kind of given to me as a proportion. 27.5% of the variation in GPA is explained by these 5 variables. So how much am I not explaining? About 70, a little over 70%. So there's still a lot of omitted variables here, right? So one thing I might be concerned with is if I'm still not explaining 70%, what could be true about these coefficients? They could be, kind of thought about that term and said there could be this bias component that exists. And the only way to eliminate that bias is if I include whatever those omitted variables are that are kind of would help explain the rest of that 70%. Just trying to paint kind of a broader picture here. So know how to calculate test statistics, determine what variables are significant, interpretations of both coefficients for continuous variables, dummy or indicator variables, and then also for the intercept. Those would be kind of the main things. The other thing that I might expect you to do, and I probably wouldn't do it for something that has quite as many variables as this does, but I might ask you to make a prediction, right? So this was the idea, let's say I only had, Oh, let's come up with I think this other example down here. Yeah, so I don't like that one as much because I know I'm not going to ask you something that difficult. So let's say that I simply had something like this. I then told you, okay, you find that the intercept coefficient is, well, let's think what makes sense here, 2.3. And maybe this is, let me think, so 0.0015. Okay. And then I ask you, what's the predicted GPA for somebody who has, I don't know, let's say, I don't know, a 900. Actually, I'm going to make the math easy on me. 1,000 on the SAT, right? Well, all you would have to do is to come up with that predicted GPA is use your coefficients and plug in this hypothetical person's value for X. Okay. Now, I might include two variables here. You would just, maybe I say, 1,000 on the SAT, and maybe the other variable we control for is, student athlete or whatever, and then we would have to plug either 1 or 0 in there. But I'll keep it a lot more simplistic. I won't kind of make these huge predictions where you've got 6 or 7 variables kind of in that regression that you have to plug in. So all I'm going to do is take that 1,000 on the SAT, multiply it by that coefficient. So that gives me what? 0.0015 times 1,000. So 1.5. However, I have to remember when I'm coming up with this prediction, even after I multiply that coefficient by that hypothetical X value, I still have to add in that intercept, right? So here, right, this kind of was 1.5, but I also had this intercept of 2.3. So 2.3 plus 1.5, this person's predicted GPA would be 3.8. Does that make sense? Questions on that? 30. Oh. All right. So some other questions that you might see on there. So the last two here, if we had a little more time, I would have dove into something like this where our units weren't kind of what we would expect. I'm not going to do that in the exam, so we'll kind of hold off on kind of interpreting this here. But one thing I do want you to know, if we have a coefficient estimate, right, we need to be careful that we don't think of it as a causal relationship, right? So we have to remember it's only ever providing evidence that these two things are correlated, right? So I might give you, something like, we know that the total number of credit hours is positively correlated with GPA. So somebody concludes that just make students take more credit hours and they'll get higher GPAs. What's wrong with that logic? Well, it's just providing evidence that they're correlated, right? It's likely there's an outside factor we haven't been able to capture, which is, maybe that people who take a high number of credit hours are also people who are able to do that, right? And maybe have a higher intellectual ability, which would also be correlated with having a higher GPA. So it's this idea that these two things are correlated doesn't necessarily mean they're causal. Right? So I might give you kind of a question like that, where I give you some logic and say kind of what's wrong with that. And really it always boils down to, it's just evidence of a correlation, not a causal effect. Okay. I might also do something like this, where you need to know that for these coefficients, we're always going to have a two-tailed test. We kind of already talked about that earlier, but it's also always coming from a student t distribution. So just to kind of review, even though I know we did it Friday, I think this is a really good thing to kind of have laid out as you're studying, right? The only time that we're going to use the standard normal distribution is if we're seeing proportions, right? The difference in proportions, or the difference in means where I know the population variance. That's when I can use that Z table or my standard normal distribution. Everything else, right? Difference in sample means when I only have sample variances, my mean difference variable, and these coefficients and their associated standard errors. All these are going to be coming from that student t distribution. Okay. I would say, if we're thinking about what we've covered since the last exam, I'm really going to be giving you examples where we're looking for the difference in two populations for both proportions, known standard deviations, and known populations, standard deviations or variances, and then when we only have sample variances. You might also have to do these mean difference problems, right? Now, really the principles of hypothesis testing are the same for all of them. So make sure you know that, for a right-tailed test, right? We're thinking about the area to the right, and my critical values are going to be positive. Left-tailed test, critical values are negative, and it's all of alpha in one of those tails, right? Either left or right. And then for my two-tailed test, right, my critical values will always be alpha over 2 is in each tail, and I'm going to have a pair of them at every alpha value or every alpha level or significance level. Also, when I'm finding the p-value for a two-tailed test, right, I can find the area in one tail, but I have to remember I need to multiply it by 2 to get my total p-value. For my one-tailed test, my p-value is just whatever area is in that one tail because I only have one tail. Okay. What's some other things to kind of keep track of? So that kind of gets us to hypothesis testing. We've kind of already talked about the types of thing I could ask you for linear regression. So there, I would think about know how to find those test statistics. That was just our coefficient divided by our standard error. Know that if our p-value is less than alpha, what we're really rejecting with linear regression is that that coefficient is equal to 0 or that there's no relationship. So if we are rejecting that, what we're actually saying is that there is a significant relationship here. So know how to look at that column for p-values. Don't get confused by those e to the negative. And then kind of doing interpretations both for your slope coefficient and also, like we did earlier, for that intercept coefficient. Okay. I also said kind of go in knowing that definition on your R squared. There could be a question about that. But really that's the scope of what I would ask you about. Right? Yeah. Yeah, so the definition of our R squared, if we're looking at some output, it tells us the proportion of the variation in our Y variable that we're explaining with all, of our X variables that we included in the regression. Okay. So if it tells me the proportion, another thing that we often see with the R squared is we see it converted into a percentage, right? So if I give you the possible answers, I might give them to you as percentages. So here, if the proportion that's explained is 0.275, the percent of the variation explained by our X variables would be 27.5%. Just moving that decimal 2 places, right? Going from decimal to kind of percentage format. Any other questions? Yeah.
How do we know if it's significant variable?
Yeah, so actually I think I have it probably written a little bit better here. All right. This is always going to be our null hypothesis, which at that there's no relationship. Right? If that slope is 0, like a horizontal line, that means as X changes, Y doesn't change at all. So we're gonna assume that there's no relationship. If the p-value is less than the alpha you're given, and right, it could be 0.1, 0.05, or 0.01. I could give you one of those levels and say, is there a significant relationship at this level? If your p-value is less than alpha for a specific variable, what you're really saying is that there is a significant relationship. I'm rejecting that there's no relationship when that p-value is less than alpha, or I'm saying there is a significant relationship. And I could even say for the SAT variable, what levels is it significant at? Well, then you would take the p-value and you would compare to each one of these and say, which of them is it less than? Another format of the question I could ask. Did you have a question?
Yeah, I was wondering, could you go over an example of finding critical values?
Yeah. So let's do, I already did one for, let me see. So let's go back here. So I think we'd done the confidence interval here and I switched back to the right exam last class. But let's say I had this example where I had CEO age, 2 different years, and I want to compare different CEOs in each year. So I've got 2 sample means, or I'm looking for the difference between these 2 sample means, and I only have sample variances. Right? So if I wanted critical values here, and I think 3 is probably is actually asking for that. Well, it's going to depend, right? So here I'm given a what type of tailed test? Right tailed test. So automatically I know my critical values have to be what? I have a right tailed test. Yeah, so right tailed test, we want alpha, whatever that is, in the right tail. So we're going to have positive critical values. For left tailed test, we want alpha in the lower left tail. So we've got negative critical values, because remember, it doesn't even matter if we're using a Z or a student T distribution, they're both centered around 0. So right tail, I'll have positive critical values, left tail, I'll have negative critical values. And they'll be the values that give me alpha in those tails. So I've got a right tail test. Right? So I could look these 3 up relatively quickly. I could do an alpha of 0.1, 0.05, and 0.01. I've got sample variances, so I should be using the student T distribution. Right? I was given an assumed true degrees of freedom of 46. So I go to that T table, 0.1, 0.05, and 0.01 were the 3 alphas I wanted to find the critical values for. Degrees of freedom was told me to be 46. So 1.3, 1.679, and 2.410, which would be these values right here. Now, if instead I had a left-tailed test, it would have been those exact same values. I would have just had to remember what? It would be those values, but negative. And then let's say it was a 2-tailed test. Well, now, for a 2-tailed test, alpha is always the area in the, I always kind of write it, is area in your tail or tails if you have them, right? So if I've got a 2-tailed test, alpha is the total area in the tails. So that means there's alpha over 2 in each tail. And I actually need a pair of critical values there. So if I wanted 0.1, 0.05, and 0.01, that would be 0.05, 0.025, 0.005. So if instead this was a 2-tailed test, these are the 3 areas I want. I'll go to that degrees of freedom of 46. So 1.679, 2.013, and I already lost the row, 2.687, right? Which I'm going to guess were probably options here. But right, we didn't have a 2-tailed test, okay? What do the values in A look similar to? I don't know if we're used to this. Yeah, if I had instead an example where I gave you population, like known population variances, well, then you could have used the standard normal, which once again, we can use that student T table and kind of cheat and just use that very last row. That gives us the standard normal values, right? So we can kind of find those in that last row. And that's how I would suggest finding critical values, even if you had, like, let's say I gave you a difference in sample proportion example, and I asked you for the critical values. Instead of hunting them down one by one in that Z table, I would just go here because the areas in the tail that you want, these are always going to be the benchmark values that we're using. And so those standard normal or Z values will be what you find in that very last row. Any other questions? Okay with those? All right. Let me think. Something else I could potentially ask. So we've done some critical values, we've done some p-values, anything else in the linear regression. What did I do? One thing that I might do is even if I don't give you Excel output, I might instead do something where I tell you the value of a coefficient, and I also tell you the value of the standard error. So if I do something like that, you can still find that test statistic by simply dividing your coefficient by the associated standard error. I may just not present it in a table format. I might just kind of list it or like give it to you. Yeah, I'm trying to think of anything else we haven't kind of covered here today or previously. I've given you kind of all the things to go over. Like I said, I would go over the practice exam A and B. If I'm thinking about the order in which I'm going to study, I would go over those two. I would look at the video for practice exam B. At the very end, I did the 3-4 additional problems on there. That would be good ones to know. So kind of go see how I kind of work through those. From there, I would probably actually look at either practice exam C or tomorrow, once I get that 5th Excel assignment out there. That's some good review of linear regression, that answer key. On top of that, I mean, if you get through all that and you're feeling pretty comfortable with everything, I mean, you could go back through and rework some of the IQ questions from the slides, but probably at that point, you're going to be pretty set, right? I would also, just as a tactic, if you haven't already started going through them, try to go through the practice exams without looking at the answers first. So especially even if you just want to start out with one, doing it that way, because then that tells you, you can then see what you really don't know, right? And those would be the ones to really focus on. And even as you go through it, like even if you're guessing, maybe like write down that you guess. So you really make sure you have identified which problems you're having difficulty with, then look at the answer key and try to be able to understand, okay, if I can rework this and understand why the answer is what it is, then that's fine. But if I still can't, then that's really going to be a topic or something that I want to review. Might be something that you might even want to reach out to me, send me an email, a question, or kind of schedule a time. I'll be fairly available tomorrow. You send me an email, I want to meet at some point. We can kind of set something up. Wednesday, I have another classes exam from 12 to 2, but other than that, we could probably find a time Wednesday as well. So I'll be looking for emails and trying to respond as quickly as possible. Other than that, any questions for me? Yeah.
How does this test compare to the other two? Like, is this the one that?
Usually people do a little better. Honestly, usually the second exam is the lowest average, just because we're doing more hypothesis testing, which we just had more time to go over it. And I think on average, most people can grasp the linear regression stuff a little bit more. And so generally I see scores be a little bit higher, and that's not true for everyone, but like on average, right? I would say it's a little bit better, yeah. No questions? So I got one favor to ask of you guys. I'm sure we're all tired of the emails if you get as many as I do. But by the end of the day, if you really could get on and fill out those student evaluations, it really helps me out. Even if you think I've got a bunch of flaws, it helps me work on those flaws. It helps the College of Business out, just getting more responses kind of does well for us with the rest of the university. So really, if you got some time today, I'd greatly appreciate, even after class, get on your phone. You don't even really need a computer. Fill those out. I'd greatly appreciate it. Okay. Any other questions for me before I let you go? Well, thanks for a great semester. I will see you guys on Thursday, 9:45. Send me an email if you have any questions, and good luck finishing up studying.